Okay, hello everyone and welcome back to your YouTube channel and welcome to this very interesting video. As you must be aware, we are recording this set of videos related with electromechanical conversion devices. And one very important element when we are designing and where we are selecting those electromechanical conversion devices is the material that is used at the core. In other words, when we are working with electrical machines, transformers, or any rotating machine, AC or DC, the material that we are using in the core is extremely important. It's very important that that material has very good magnetic properties in order to reduce the magnetic losses. As we reduce the magnetic losses, of course, the total efficiency of the electromechanical conversion device will increase. So we need to be careful when we are selecting or specifying the magnetic material. And today we have a very simple, in general way, it's a very simple example, numerical example, but at the same time, the idea of this example is to make you reflect about the concepts. So here there is a problem statement. As you can see, an application requires a magnetic material capable of operating at a flux density at least be equal to Teslas, and not retaining any significant remnant magnetism. As you can see over there, I use italic letters in order to highlight this, but let me use this yellow color over here because this is a very important part of your solution, okay? Now the question is, what material could be considered? And here in figure Q3, in this figure over here, you have the survey of magnetic material. And as you can see, the vertical axis, on the vertical axis, you can see that we have the saturation magnetisation. And on the horizontal axis, you already have here the coercivity values. As you can see, the magnetisation is in Teslas, and you recognize that there is a beautiful number 2 over there. So we want material at least above 2 Teslas. So that is one key, a very important key here for the selection of the magnetic material. On the horizontal axis also, we need to have very important information. Because if you remember your classes when I was talking about the magnetic strength and those ammeters over here, there is a classical division between soft magnetic material and hard magnetic material. So some books include a third class that is typically between 1000 ampere meters and 10,000 amp meters. But what you need to understand is that this hard and soft material define if the magnetic material will retain or not some magnetism. So what I want to do is to solve this very basic problem for my students. And the solution, to be honest, it's extremely simple. Because what we need to do is basically, okay, this vertical axis, I will go here with a straight line, defining 2 Teslas. And as you can see over here, we have 3 candidates. The first candidate that is extremely visible over here is the iron, and the chemical description is Fe. And on the other hand, we have here the silicon iron that is probably one of the most used ferromagnetic material. And on the top, I use red color over there for what we call the cobalt iron. Now, the question is, okay, all these three different materials, all of them can work above 2 Teslas. So one of the criteria is already used. However, what is very important for us now is to identify the difference between soft and hard material. Because in this problem statement, we were required to have an operating flux at least 2 Teslas, but we don't want any significant remnant magnetism. So we don't want hard materials. We don't want hard materials because they tend to retain those magnetic properties. So in this case, we can see that on more to the left right, we can see over here in green color the silicon iron, and that means that this material will have the less remaining magnetism. So we can exclude the cobalt iron because this material will tend to remain with some magnetism, and we don't want this in this application. We don't want the classical iron because it's a material that also is harder than the silicon iron. So the proper answer over here is yes, let's go for this silicon iron that also is one of the commonly used iron for magnetic cores. So again, you can see it's a very simple example. However, this will define the type of applications that you can, the type of applications that you can perform with different group of material. I highly suggest at home that you start to look different combinations, but it's extremely important also that you understand the difference between soft and hard materials. Well, this is all for this very basic video. I hope you enjoy, and I will see you at the next one. Bye now.